For those of us who watched Jurassic Park, we can remember how Alan Grant would oftentimes remark on the similarities between dinosaurs and birds. However, what took me longer to realize is that birds really are living dinosaurs. Looking at the fossil evidence, we can show the transition from dinosaur to bird over millions of years. We can look to Archaeopteryx, in the period in which birds first began to show up on the scene. We can see remnants of theropod origins in living birds and begin to unfold their story of evolution. So, when did dinosaurs become birds anyway? The story isn't quite as linear as we might be led to believe. So, birds didn't occur after dinosaurs. They actually grew alongside them for millions of years. What I had assumed is that birds only evolved after dinosaurs. But really, birds are the only surviving group of dinosaurs. They're called the avian dinosaurs, and they grew alongside the non-avian dinosaurs, which are traditional dinosaurs. Broussard et al. Describes birds evolved from theropod dinosaurs during the Jurassic, around 165 to 150 million years ago. About that 150 million years ago was Archaeopteryx, one of the first known birds. And it lived in the late Jurassic, and there would have been other birds like this, but this is the one that we know of. It's the most famous. And so these first birds continued to evolve and diversify over the late Jurassic and early Cretaceous, and then even on to today. This image from Springer Nature Journal depicts several dinosaurs and birds alike. These dinosaurs in the middle are more bird-like, and they evolved throughout the Jurassic and Cretaceous. While not all non-avian dinosaurs went extinct with the asteroid and the consequences that came after, avian dinosaurs survived and were able to diversify throughout the Paleocene into birds today. While the depiction of evolution is often seen as a straight line, it's more of a branching situation, and these few species were able to diversify and become the birds we see today. So let's dive deeper into where we first saw the transition from dinosaur to bird with the Archaeopteryx. So Archaeopteryx has feathers and wings like a bird that help to support flight. Just for context, the Schiltz Audubon Nature Center explains that bird wings and feathers, the feathers specifically, they have this kind of asymmetrical structure with this aerodynamic design. And so the front edge is called the leading edge, and it's kind of this wider edge that, when paired with the trailing, narrower side, it allows for this flexible yet stable structure without weighing down the Archaeopteryx's skeleton, or a bird skeleton, really. And so this is one of those big traits that they have in common. It's just this huge indicator that dinosaurs kind of grew into birds, or birds are a group of dinosaurs. Birds also have curved wings, and this structure is known as an airfoil. This aerodynamic structure is able to generate lift and reduce drag. The Schiltz Audubon Nature Center describes these wings as having a wide front and a narrow back, and this design is able to split the air over the top and the bottom of the wing. Over the top, fast air travels, and over the bottom, slow air travels. And this slow air at the bottom creates a higher pressure, and that higher pressure lifts up on the wing and generates lift for the bird. Looking at the layering of the wing, the Archaeopteryx of the Ecology of Archaeopteryx noted, the large tertial tract all indicate Archaeopteryx was capable of volant locomotion. This tells us that Archaeopteryx had this primitive leading edge, and this suggests that it would be capable of some kind of powered flight or glide. And we can even see that in this paleo art here, with this thicker edge tapering out into a thinner edge. Even today, evidence of birds' dinosaur lineage is still displayed through homologous features. Using anatomical features such as the ankles and wishbones, we can point to this as evidence for theropod history. The wishbone in birds is formed by the fusion of collarbones, and the wishbone provides an attachment point for flight muscles, according to Britannica. Originally thought to be unique to birds, it was found that the ancestors also had wishbones, but for a slightly different purpose and appearance. We can see several theropods had wishbones, such as Archaeopteryx, Velociraptor, and even T-Rex. They all had the same fused collarbone. And this provided a point for muscle attachment, but more for bipedal locomotion versus flight. Cal et al. Explains the wishbone had points for attachment for ligaments and cartilage in the chest and shoulder region for forelimb structure and function. The wishbone in theropods, it's reasonable to conclude that it was passed down to birds and adapted for flight versus just spawning in birds. Another point for comparison is that birds inherited this same theropod ankle, although it doesn't look like it at first glance. This in theropods is called the astragalus, and it has this ascending groove, and this is called the ascending process. It doesn't look like birds have it because all of these bones are fused into the tarsometatarsus. However, a study from Osafuentes et al. Explains, unexpectedly, we found the ASC derives from the embryonic intermedium, an ancient element of the tetrapod ankle. In layman's terms, this means that the embryos were found to have the ascending process. It's found in various birds, and this provides us another linkage to dinosaurs that was previously thought to be non-comparable. So while Jurassic Park's runtime may not have had time to discuss the ASC's evolutionary timelines, it did still emphasize that dinosaurs have more in common with birds than we originally thought. The long history of dinosaurs lives on in birds today. We can see traces of the past through Archaeopteryx, the millions of years spent alongside their dinosaur cousins, and rediscovered through modern techniques. Birds are descendants of dinosaurs, but not only that, they're the only dinosaurs still alive today.